view problems of curvilinear motion of a particle using x and y coordinates. And we'll begin with this one. Here we have a particle which moves along this parabolic path, and the position of the particle as a function of time along the x-axis is given. See if you can find the x and y components of the velocity and acceleration of the particle when the time t is 1 second. Well, to solve the problem, we'll use these two key equations to relate the velocity of the particle in the y direction to that in the x direction, and the acceleration of the particle in the y direction to that in the x direction. First, though, let's discuss the motion along the x-axis. Its position can be determined from this equation. In other words, we have 3 g squared plus 2, and all we do is evaluate this at the time t equaling 1 second. And doing that, of course, we get 5 meters. So the particle is located over a distance of 5 meters at the instant t is equal to 1 second. Now we'll get the velocity of the particle in the x direction, and that's found by simply taking this time derivative, and we get, of course, 6t. We evaluate this at the time t equaling 1 second, and of course we get the answer of 6 meters per second. Finally, we get our acceleration by taking another time derivative. We get 6 meters per second squared, a constant. Now let's discuss the motion in the y direction. First, the position, and that can be found, of course, by simply evaluating this equation. In other words, 0.25 times x squared. And of course, at the location x equaling 5 meters, we get our result, and it turns out to be 6.25 meters. So the particle is located up a distance of 6.25 meters at the instant t is equal to 1 second. Now we'll get the velocity component in the y direction using this equation. We need dy dx. That's found from this, isn't it? In other words, 0.5 times x. And of course, x is equal to 5. Therefore, I'll put that in here. And now x dot. X dot is 6. At the time t equals 1 second, of course. Running through the calculation here, we get our result of 15 meters per second. So we have the particle moving at 6 meters per second this way and 15 meters per second this way. When we find the resultant velocity, it will be tangent to the path at the time t equaling 1 second. Finally, we'll find the acceleration component in the y direction, and we'll follow this formula. We have to take the second derivative of this expression with respect to x. First derivative, of course, gives us 0.5x, and the second derivative will give us 0.5. Next, we multiply that by x dot squared. In other words, 6 squared. And finally, we add to this the derivative of y with respect to x. And that, of course, would be equal to 0.5x, and of course, x is equal to 5. So we'll write this as 0.5 times 5. And finally, we put in x double dot, which is 6. If you work this out, you get your result, and it's 33 meters per second squared. To summarize then, the particle has an acceleration component in this direction of 6 meters per second squared, and another component going up at 33 meters per second squared. When we add these up vectorially, the resultant acceleration will be directed up somewhere in here, and of course that's in toward the curvature of the path. All right, now consider solving this problem. See if you can determine the x and y components of the velocity and acceleration of a particle when the time t is 1 second, if the path that the particle is moving along is y equals x squared plus 3x, and motion along the x-axis is equal to 2t squared. Well, to solve the problem, again, we use these two key equations to relate the motion in the y direction to that in the x direction. And then to begin, I would find the motion along the x-axis. First, writing out what x is at the time t equaling 1 second, which of course would be equal to 2 then, taking the time derivative of this function and getting x dot, and then x double dot, evaluating at the time t equals 1. You get these results when you're through. Next, I would find the position of the particle along the y-axis, although in this problem it's really not necessary to do this part. Taking the time derivative, though, we'd have to use this relationship. Again, dy dx would have to be found from here, and then you'd multiply it by x dot, which is 4 meters per second. And finally, I get the acceleration component in the y direction by taking the second derivative of y with respect to x from here and evaluating it at the time t equals 1 second, and also putting in x dot squared. That would be 4 squared, of course. And then you'd have plus dy dx from here times x double dot, which was 4 meters per second squared. Doing the calculations will give us these results. And so I haven't finished the problem then. We'll now end our review.